The difference with a detergent is they are metallic soaps. They are things that we call sulfonates or phenates or salicylates. And I'm a mechanical engineer, so I actually don't really know the details exactly of what they are, but I do know how they work. And the way a detergent works is it's what we call surface active. It goes to the metal surface and lays down a protective layer on the surface of the piston or whatever, and prevents deposit precursors from adhering to the piston, causing deposits that can cause ring sticking and so other problems with the engine. However, because these are metallic soaps, calcium sulfonate, magnesium sulfonate, phenate, whatever, when they are burned, they do leave behind a residue or an ash. And this is measured as sulfated ash. It's an ASTM procedure D874. You take a measured weight of oil, put it in a crucible, react it with sulfuric acid, and burn it. And what happens is all of the hydrocarbon components burn off, and the metals are converted to sulfates. And you measure the weight of these sulfates compared to the known measured weight of the oil sample, and that in a CJ4 oil has a maximum limit of 1% of the oil can form sulfated ash. The Suprex Gold ESP products have a unique detergent blended system that combines calcium and magnesium, combines sulfonates and phenates to give one of the highest detergent base numbers, which is the ability of the oil to neutralize acids for a given sash level. Again, that's a designed-in component to provide an added advantage of better acid neutralization while still staying within the 1.0 maximum sulfated ash limit. Next slide. The reason we have to worry about acid neutralization is we do have acids coming into the engine. Fuel, even though today it's at 15 parts per million, very low, does still contain some amount of sulfur, which when it burns can make sulfur oxides, which can react with water vapor and literally manufacture sulfuric acid. It can happen in the oil. It can actually happen in the combustion event. And as I had said earlier, it can happen inside of the EGR cooler when we pull some of the EGR stream off and run it through this cooler. If you happen to drop below the dew point, which can happen under certain ambient conditions, the water vapor can actually condense, and you can manufacture sulfuric and nitric acids in the EGR cooler, which you then dump back into the engine. On the other hand, oxidation byproducts, kind of blow-by gases, and actually the oxidation of the base oil itself can result in weak organic acids that tend to go after lead components in the engine. In fact, in the MAC T12, which we'll talk about in a couple slides, one of the primary pass-fail parameters is the amount of lead solubilized out of the bearing overlay in the engine. And the way that you handle or formulate for that is not necessarily by using more detergent base number. It's actually by using a better antioxidant package which prevents the base stock oxidation and prevents corrosive attack of the bearings. So total base number it's a relative term. It's a number derived by actually titrating acids and bases in the held in the oil. And because oil is oil. It's not aqueous. And water, acids, and bases react very rapidly because we're in polar media. But an oil is a nonpolar media. So it's actually possible to have a basic something and an acidic something floating right beside each other in the oil. And if they can't get together, well, they float there independently. So an oil can have both a total base number, which is a measure of how much acid the oil is still able to neutralize, and a total acid number, which again is a titration and is a measure of the acidic components in the oil. Typically, as I had kind of indicated, these are organic acids. So let's go to the next slide. These are some actual field test data taken in some 450 horsepower Cummins ISXs, where we monitor both TBN retention and TAN growth, and we look at the both the Suprex 1540 and the full synthetic 5W40. And personally, I detest the idea of talking about TAN, TBN crossover because it's an absolutely meaningless thing. I mean, fresh oil has a total acid number. Some of the additive components can be measured by the TAN number. It doesn't really mean anything. As long as the total acid number remains relatively flat and under control, and the total base number remains sufficient to work, any crossover between TAN and TBN is absolutely meaningless. Back in the mid-'80s, I formulated some very specialized 5-TBN 0.5 sulfated ash lubricants that ran for 30,000 miles with the total acid number higher than the total base number, and the engines ran just fine. The real measure is if lead remains under control. And in all of these units, although we don't have it plotted, lead was staying well below 20 parts per million out to 60 or 70,000 miles. What Cummins recommends is they don't actually look at TAN, they look at a hard cutoff for TBN when it either reaches half of its original value or 2.5 TBN as a absolute hard cutoff where the oil has to be changed. And in those cases, if you look at the extensions of the lines, you can see that we are well beyond 50, 60, 70,000 miles before the total base number would be getting to the point that we would have to say, yes, the oil is condemned and has to come out of the engine.